This course on DC motors will familiarize you with the basic parts of a motor and the many principles of DC motor operation. You will learn to identify the types of motors, how the field, armature, and commutator are constructed. You will also see the many ways in which motors can be wired to do their jobs. You will learn the proper ways to maintain motors and how to troubleshoot motors by doing some actual troubleshooting problems. This is a cutaway version of a DC motor. This is the armature. In DC motors, or machines as they are sometimes referred to, the armature is attached to the rotor shaft. This is the armature core. The core is made from many silicon steel laminations. This type of core allows the easy passage of magnetic flux. It also has great mechanical strength to withstand the high speed of rotation and vibrations caused by a load. The slots in the armature can be open or partially closed, depending on the type of armature winding and the size of the machine. Open slots are used when the armature coils are wound separately and then installed in the slots. Partially closed slots are used on motors where the conductors are wound turn by turn directly on the core. This is the stator, or stationary part of a DC motor. The stator contains the field of the motor, the non-moving part of the magnetic circuit that makes the motor function. The stator has a frame or shell, winding supports, ventilation slots, and temperature detectors if used. If the motor has a base attached, it is not considered part of the stator. This is the commutator, which is really just a switch that turns the current on and off to each winding of the armature. The brushes that ride on the commutator provide the current path to the armature. To make the motor turn, there are two magnetic poles, north and south, in the magnetic circuit of a motor. The poles in the armature must provide maximum attraction with the poles of the stator. When current is applied to the armature, the current creates a magnetic field that interacts with the magnetic field of the stator. As the armature turns, its magnetic field must be changed constantly so as to provide continued attraction with the magnetic poles of the stator and therefore rotation. The commutator segment provide the switching for the armature field by connecting the armature current at the brushes to the correct armature coils. As the motor turns, the commutator connects the armature current to each individual coil of the armature in succession, providing a smooth magnetic attraction between the poles of the armature and the poles of the field. There are many applications for DC motors, the starter for any car or truck. Under the hood of the vehicle is a complete set of DC motors, including this one for the windshield wipers, or this one that operates the heater and air conditioning blower. Motors raise and lower windows and raise and lower the antenna. An elevator drive motor is one example of a large DC motor. Other DC motors might move loads along a conveyor belt system. DC motors perform a great many functions, and each application is designed for its unique load, torque, and control requirements. Each application is unique in design and may use a DC motor. However, many modern applications might use AC motors. Always be sure what kind of motor you are working with and what its ratings are. If a conductor carries a current, magnetic lines of force are created around the conductor, which create a magnetic field. The direction of the current in the wire determines the direction of these lines of force. If a compass were placed next to the wire, it would indicate the direction of the lines of force. If the current direction is changed in the wire, the magnetic lines of force will reverse, and the magnetic field will reverse. When the wire is placed in another magnetic field, the magnetic field of the wire would react, with the outside magnetic field creating a force. This force is called motor action. If the wire were free to move, as the armature coil of a motor, then the force would cause the coil of wire to move and turn the armature. This is how a DC motor works, with the commutator supplying the proper current direction to the proper armature coil, ensuring continued motor rotation. The armature is composed of many coils of wire, and each coil has two ends. But let's look at a single end of one coil. There is current flow in the wire, magnetic lines of flux from the field coils, and a force created in the wire. In order to find the direction of the force on the wire, the right-hand rule is used. The right-hand rule shows that if the direction of the electron current in the conductor is the direction of your second finger, the direction of the stationary magnetic field is the direction of your first finger. Then the direction of the force on the wire will be in the direction of your thumb. If the current is in the opposite direction, as it would be on the other side of the coil, then the force would be in the opposite direction. The entire loop of the armature then would look like this. For a given current direction controlled by the commutator, there would be an upward force on this side of the coil and a downward force on this side of the coil. These forces work with each coil of the armature and turn the motor. The principles by which a motor operates are, in reality, quite simple. The simple force rule, the right-hand rule, shows why the motor rotates and how the motor action works. Now let's review. This is the current direction in this single loop armature. Which direction is the force on this side of the loop? That's not correct. The force on this side of the armature loop must be in this direction for the loop to rotate clockwise. Now, which direction is the force on this side of the coil? Direction for the loop to rotate clockwise. Now, which direction is the force on this side of the coil? Very good. The force on this side of the armature loop must be upward for the loop to rotate clockwise. In this DC motor, where is the armature? You've got it. This one. The armature is the rotor in a DC motor and transfers the rotational force created in the motor to the load. If the armature transfers the motion to the load, what function does the commutator perform? Well done. Right. The commutator works with the brushes to act as a switch, supplying the proper direction of current to the proper armature coil. A series DC motor is the simplest type of motor. The armature, which is free to rotate, is composed of many turns of wire, connected through the commutator and brushes to the current powering the motor. The field windings of the stator generate the magnetic field for the armature to turn in, and are also connected to the current powering the motor. These coil ends on the armature are connected to one side of the line current through the commutator, and these coil ends are connected to the other side. This is how a multi-coil armature is connected. All of the coil ends on one side are connected together, generating a force in one direction. And these coil ends, with current flow in the opposite direction, generate force in the opposite direction. As the rotor turns, the armature coils are switched from one side of the source current to the other. Because of the way the armature coils are connected to the current source, the motor will turn as soon as current generates a magnetic field in the motor coils. Now, try this one. If the motor rotates counterclockwise, which side of the armature would have an upward force created in it? Very good. Right. This is the side of the motor where the force would be upward. Now, what would happen if the direction of the flux were changed? That's right. Wrong. The flux will be in the opposite direction, and the motor would rotate in the opposite direction. The permanent magnet motor with modern magnets can be made with flux densities approaching the electromagnets of wound coil motors. PM motors can be mass-produced very inexpensively. Their drawbacks are they are subject to demagnetization by overload currents, and there is no control over the field. What material is normally used for motor magnets? That's not right. PM field motors normally use ceramic cast magnets. From what material is the outer sleeve of a PM motor normally made? Very good. Not right. The field frame is normally made from steel tubing. Where is the field frame on this PM motor? That's very good. Look again. The field frame is actually the case on this PM motor. One more. Where is the ceramic magnet on this PM motor? Well done. That's wrong. This is the ceramic magnet, the field of this PM motor. Here are the wiring diagrams or schematics of a shunt-wound motor, a series-wound motor, and a compound-wound motor. Which is the series-wound motor diagram? That's right. You missed it. This is the diagram for the series-wound motor. A series motor is often known by another name. Which is it? Well, that's not right. Varying speed is another name for a series motor because motor speed varies with the load. Only one of these uses would not be appropriate for a series motor. Which is it? You have it. A pump is not normally a variable speed application. A series wound motor, then, in general, is best suited for which type of application? Very good. Right. The series wound motor produces high torque under load and increasing speeds when the load is reduced. Which of these is the diagram for the shunt wound motor? That's correct. The wrong one. This is the diagram for a shunt wound motor. Shunt motors with a field control are called adjustable speed motors. What are they called when they do not have a field control? That's right. That's not it. Without a field control, a shunt-wound motor is a constant speed motor. As a constant speed motor, the shunt-wound has many applications. Which of these is not a good application for a shunt-wound motor? That's right. That's wrong. A hoist is an application for a series-wound motor with its high torque and variable speed, rather than a shunt-wound motor. Touch the part in the shunt motor diagram that will vary the speed of the motor. That's not right. This rheostat or variable resistor controls the speed of the motor. Which of these is the diagram for the compound wound motor? Very good. Wrong. This is the diagram for the compound wound motor. A compound wound motor has two coils that are not found together in any other DC motor. What are they? You got it. Right. The compound motor is the only motor containing both the shunt field coil and the series field coil. The compound wound motor has the same high torque characteristics of what other type of motor? Well, that's not correct. The compound motor has the same high torque characteristics of the series wound motor. This diagram is typical of a DC motor. There are series coils, shunt coils, and commutating coils. Which are the series coils? Nicely done. These are the series coils. Which set of coils would be used in both this compound wound motor and a typical shunt wound motor? That's wrong. You should review the topic in the workbook and try this exercise again. Which set of coils would be used in both this compound wound motor and a typical shunt wound motor? That's right. These are the shunt coils, which are also used in a shunt wound motor. There is one set of coils left on this diagram which you have not identified. Which of these are the interpole coils? That's wrong. You should review this topic in the workbook and try this exercise again. There is one set of coils left on this diagram which you have not identified. Which of these are the interpole coils? That's wrong. You should review this topic in the workbook and try this exercise again. In this compound wound motor, there are 4 poles. Each pole is wound on a separate core and can be seen and counted. Let's look at 2 field windings with pole pieces and an armature. When there is no power applied, the armature moves freely. There is no magnetic force being created in the motor. Without the commutator connected, when power is applied to the motor, the armature moves between the field poles and stops. When the armature is moved, it moves back to its original position. The force of the magnetic field created by the field windings and the poles causes the armature to move and return to that position if disturbed. If the current is reversed, the polarity of the field poles is reversed, and the armature will move into the opposite position. When the commutator is connected to switch the current in the armature, and power is applied, what do you think will happen? Right. No, watch. If the commutator is connected and power applied, the armature will rotate. What will happen if the leads to the commutator are reversed? Good choice. No, think again. With the commutator leads reversed, the armature will turn in the opposite direction, counterclockwise. On larger DC motors above 1 horsepower, interpoles are placed between the main poles of the field. They assist the commutator in changing current direction in the armature by assisting with the changing flux. How are the interpoles spaced around the armature shaft in relation to the main field poles? That's right. Wrong. The interpoles are equal to the main field poles in spacing around the armature shaft. In this compound motor, are the interpoles in series or shunt with the armature? Very good. That's not right. The interpoles are always in series with the armature and carry the same current as the armature. If the interpoles do not work properly, what will you see happen at the commutator? You missed it. If the interpoles do not work properly, sparking will be seen at the commutator like this. These are the armature coils of this DC motor. There are 2 ways the armature coils are produced: random wound and formed. How are the random wound made? That's not right. Random wound coils are wound directly on the armature, while formed coils are made on a form and placed in the armature slots. Because the windings of this random wound armature are compact and close to the shaft, the armature is considered to be excellent for what applications? Good job. That's wrong. High-speed applications are the best for the compact, random wound armature. The formed coil has its own set of advantages. One is that the coil is sealed against dirt and moisture. What is the other? Very good. That's wrong. Formed coils can be replaced very easily if they are shorted or damaged. Each type of armature is suited for specific applications. And when you are working with any motor, make sure you know which type of armature is used so the correct repair procedures can be used. The armature core or rotor must have several properties. Among these are mechanical strength and low hysteresis losses. What is another? Correct. You missed it. The armature core also must have high electrical resistance to insulate the coil windings. When a voltage is induced in the core by the coils, eddy currents will be produced in the core material. These currents can be reduced by... That's right. Wrong. Laminating the core will reduce eddy currents by creating much shorter paths for the currents. Here, you can see the laminations of this armature, which are about 1/64 of an inch thick. These laminations are fastened together with a shoulder and shrink ring. What is another way the laminations can be held together? That's correct. Another way of holding the laminations is by riveting them together between the end plates. Here is the commutator for this DC motor. This is the face of the commutator segments where the brushes rest. And this is the neck or riser, where the leads are soldered onto the bar. Each segment of the commutator is separated by what kind of insulator? That's right. Wrong. Thin strips of mica are used to insulate the commutator segments. Now touch the part called the V-ring, which holds the commutator segments in place. Well done. This is the V-ring, which holds the commutator segments in place. If the brushes fail to make solid contact with the segments of the commutator, sparking will occur. What is the process called to prevent this from happening? That's good. Not right. Undercutting is used to help the brushes make better contact and prevent sparking. Even though undercutting is used, if dirt builds up in the slots, it may cause short circuits between the bars. This ring fire can be prevented by using a special tool on the commutator slots to remove the dirt. The commutator segments are connected to the armature of a DC motor by soldering or welding to the slot in the commutator segment. When the armature is made at the factory, the leads are soldered or welded to the commutator bars. Great care is taken to see that the commutator segments are not allowed to become too hot when the connections are soldered or welded. Excessive heat can ruin the insulation between the segments or loosen the segments. When inspecting a motor that has developed a problem, be sure you check the coil connections at the commutator for any signs of shorting, breakdown in soldering material, or a mechanical failure, such as the connection being broken. This is a good visual inspection of these items that doesn't take much time, but could quickly locate a problem. The brushes of a DC motor rest on the commutator. The brushes make contact with the commutator, which feeds current to the armature. Because this brush is one of the key parts of a DC motor, the brush should have high contact resistance. This will do what? Well done. Right. The brushes should have a high contact resistance to prevent sparking. When the mica insulation between commutator segments is undercut, what type of brushes should be used? That's not correct. The brushes should be non-abrasive when the commutator has been undercut. Brushes with abrasive materials should polish the commutator segments. What color should the commutator be if the brushes are polishing properly? That's not right. The commutator should appear a chocolate brown color if the brushes are polishing them properly. A brush used in a low-voltage, high-current application will have what added to the brush material? A low-voltage, high-current brush often has copper added to decrease the contact resistance. This diagram is typical of a DC motor. There are series coils, shunt coils, and commutating coils. Which are the series coils? Nicely done. These are the series coils. Which set of coils would be used in both this compound wound motor and a typical shunt wound motor? That's wrong. You should review the topic in the workbook and try this exercise again. That's right. These are the shunt coils, which are also used in a shunt wound motor. There is one set of coils left on this diagram which you have not identified. Which of these are the interpole coils? That's wrong. You should review this topic in the workbook and try this exercise again. Very good. These are the interpole coils. That's wrong. You should review this topic in the workbook and try this exercise again.
Before starting the first lesson, let's review how action code works. The system uses a workbook containing barcodes, a scanning wand, a video disc and disc player, and a touch-sensitive video monitor. The workbook is your key to watching the video material. It contains the barcodes which appear at various points in the lesson. When you scan the wand over a barcode, hold the wand straight up and move it smoothly with the tip touching the paper. That sound means that the scanning wand was used correctly. But when you hear this sound, you need to scan the barcode again. Ready to align the trace vertically? Touch here. The touch screen makes Action Code especially interactive and easy to use. In making your touch screen responses, use your finger or the scanning wand. Touch the exact point on the video screen that indicates your answer. You are right. The image is out of focus. Remember, you can use a barcode anytime to control the video. You can interrupt a sequence to go back to the beginning or to another sequence in the same lesson merely by scanning a barcode.